All right, so for our first problem here, we're asked to find the product, and note that it doesn't say to write out the mechanism, so I won't do that for this one. But, so this problem, our reactants are Br2, NaOH, and H3O+. And as you already know, NaOH is going to act as a base. I'm just going to write that up here. So that's going to steal one of the hydrogens here next to the carbonyl group. And then the now enolate is now going to react with the Br2 and then eventually go through that 3 times. And it's going to form the product with the same R group. So it's going to have this, but instead there's going to be an OH there, making a carboxylic acid group on there. And not sure if you can see that. But that should be the product. All right, so for our second problem here, we are asked to draw the mechanism and write out the product as well. So here's our starting material. You see up here, we have a carbonyl and also an ether group, and it's reacting with KOH, H2O, and H3O+. So for this one, the potassium here is going to just be a spectre ion, and there's going to be like a minus charge here on the OH. And so this is going to come down right up and attack the carbonyl group. This is going to go up. Sorry, that's really bad. It's going to go to that oxygen. And so what we get over here is same group. Well, pretty similar. Get O minus up there, where the double bond used to be. Still have the same T group over there, and now we have an OH on here. So that's going to lead to that. And so then the minus charge is going to come back down, make that double bond again, and this group will leave. And so down here, we will have same group. This will be double bond again. That group is kicked out, and we have OH here. And then, so then that will form also when this group is kicked out. There will be an O minus right over here. And because of the acidic conditions that it's in, this is going to go ahead and steal this hydrogen there, making this over here. Let's see. Yeah. So then there'll be an O minus there, and this will also have the hydrogen now. Sorry, let me just fix that. Just to be better. So here is where the that will lead to, and hopefully you can see all this. I will show it later if not. But then all this will react with the H3O+, or not all of it, but this will go over here and take a hydrogen and form the final product, which should be, kind of going down here. All right, let's see. So that will bring back the hydrogen there on that carboxylic acid group. And you also have this as well. This should be the final product for this reaction. So yeah, just show the whole thing in case it's hard to see. All right. So for our third problem here, we are asked what produces this product. And this one here is a multiple choice, so we have a few options here. So up here is the product, and we are supposed to find which of these reactions will lead to that product. So starting with A, it looks pretty promising, with the NaOH acting, and we'll go up there and do the NaOH will act and it will attack the carbonyl group, which will then kick this group down. Since it's in a ring, it'll all space out. So that could be right, but let's move on to B. With this one here, it already starts in this form that looks very similar to this one, not in the ring form. But however, the CH3OH will react differently, and it won't produce the extra carbon on this that we need. So down to C, this one also looks pretty similar to A, almost exactly the same, except there's the carbons on this one instead of this one, or the extra substituent, I mean. So it could be either A or C, depending on it. D is Gabriel synthesis sort of problem, so it could be this one. The KOH will react with the NH, kind of act as a base for that one, but it doesn't look like it's going to form the chain of carbons that we need. So let's look back at A and C, and we could tell that it's either going to be one of these two. And if you could just think in your mind about it, or you could write out the whole mechanism if you want to. The OH here is going to go up to this carbonyl group and do this sort of thing. And eventually it's going to go back down and kick out this group. And so the way I see it here is that this substituent is going to be still right next to the carbonyl group, which is exactly what we want. So the correct answer here has to be A. Okay, so for problem number 4, we're asked again to predict the product of this reaction. And so with this one, here's our starting material. Our reactants this time are H2O and H+, just signifying acidic conditions. So with this one, the mechanism is kind of long, but it doesn't ask for that. So because it's in acidic conditions, this oxygen up here is going to react with the acid, and then it's going to go through the whole transesterification process. So this is the transesterification reaction. And so, if you just know the mechanism, it's not required in this problem. So the product that's going to be produced is pretty similar. It's going to eventually kick off that ester group there, and there will be an OH instead. So it will simply form a carboxylic acid group, and this group will leave due to this process. So, I hope that's clear. Let's just show this. Moving on to problem 5. This problem asks us to write out the mechanism and the product for this reaction. So this one is going to be a little bit more involved than the last one, but it's actually fairly similar to problem 4. This time we're just writing out the mechanism. Alright, so got over here the starting material, and then we have an OH group attached to carbon chains, and we also have an acid down here. So this oxygen up here is going to grab one of the hydrogens down there, and then it's going to form this product. Or not product necessarily, but there's going to be a positive charge on this group, and then it's going to react with the OH group. So this lone pair is going to come over here, and it's going to attack the center, the carbon center, and one of these are going to come up and neutralize the positive charge on the OH there. So I'm just going to write it out over here. That'll cause that group, that over here, and then I'll just write it down here. going to be an OH. Make sure not to forget any carbons. So now, this is what's going to be there, if you could see it. So now there's going to be a positive charge on that OH group that attacked. And so, if you have an excess, if this is an excess, which we're going to assume that there is, it's going to react again with the same carbon group with the OH here. And that's going to go ahead and take that hydrogen and act as a base, so it can neutralize that charge there. And so, this is kind of weird, but bear with me. Got OH up there, OH over here, and now we have just this ether group here, along with those. So now it's fairly neutral on charge. But now this is going to react with the acid again. This acid over here, this OH is going to come over, steal one of those hydrogens from the acid, and then it's going to form this product. Give me 1 second. Okay. So now there's this OH2, or water, and it's not going to want that there, so it's going to kick out that group, and then it's going to form this product over here. So now I'm just going to move that group up. So that's what comes from that. But now there's this, there's going to be a positive charge on that central carbon there. And so, to help neutralize that, this OH group up here is going to come, and there's going to be, that lone pair is going to come down, and it's going to form this product here. We're almost done. But this does take a while, so. Yes, so now we have another positive charge up here, where there's this OH group right here. And so that's going to react again with, what is it? Oh, with your starting OH group. So if you still have more of this, over here, that's going to come and take that hydrogen there, and then transfer that lone pair, and you're going to get the final product here, which is that. Yep, so that should be the whole mechanism, and this should be the product right down here. Goes through the whole transesterification process again, or the Fischer transesterification. So, hope that's clear. I will show it if it's not, but all right. All right, on to problem 6. So this one asks, which of these reactions is going to form this product right here? And so, as you can see, there is a benzene ring, and there are two groups, two substituents attached to it. So, now our choices are these reactions below. This is another multiple choice. So, looking at choice A, it goes through this reaction with the Cl and the carbonyl group in ether attached with FeCl3. So we know that will put the substituent on any of these, doesn't really matter. But then reacting with the Br there and making sure that you know that it's going to go through a hydride shift. So this will turn into like an isobutyl group. But since this one is first, we know that since this one is a meta activator, it's a meta group, and so any substituent added after that will go onto the meta side. And as you see up here, these two substituents are both making a para form. So this one can't be right because it's going to go and attach to the meta group. And so looking at B over here, we see that it's reversed. So the Br group will attach on there first. And since it is orthopara substituent group, that means the next group will attach via ortho or para. So this is possible. With choice C, we have that we already have a substituent on here, and so going through this reaction, this will go and attach via on the meta side, and then that one will go as well. And that will create 3 substituent groups. So this one can't be it. This one has extra substituent as well, just a methyl group on there. So, but once again, this will lead to 3 substituents, and that's not exactly what we want here. So that means that the correct answer has to be B. This is the only one that will go and make the para group. Now, it could be noted that that this reaction could lead to ortho substituent as well. But since this is the only plausible option, B has to be the correct answer. Okay, on to problem 7. This one asks, which uranium ion will be the most stable? And so this one's another multiple choice. Got 4 options here, with option A being the positive charge is on that carbon right next to the alcohol group. Option B, the positive charge is over here on the left side, kind of away from everything. Option C is pretty similar, just on the other side. The partial positives over here, the positive charge. And then option D, it does a double bond there, so the positive charge is on the OH group, which donated a lone pair. Basically going from choice A, and then like moving that lone pair here. Let me just put this there. That goes down and neutralizes the positive charge there. So which one of these is going to be the most stable? Well, you can already rule out B and C, because these ones, the positive charge isn't near the group that could resonance with it, so it's not going to be option B or C. Option A seems very promising. However, the most stable group is going to be option D because of the resonance that the alcohol group has with the uranium ion. So this one, choice D, is going to be the most stable because of that. On to problem 8. This one's asking for us to write out the mechanism and the product or products for this reaction. So what we have here to start with is benzene ring, and then that first reacts with Br2 and FeBr3, and then that's going to react with SO3H and H2O. So for starters on this mechanism, we're just going to come down here, and so to start, we know that the benzene ring cannot react with just Br2. It has to be a very strong electrophile, a very large positive charge in order to react with it. So the Br2 is going to react with the FeBr3, and so this is going to go over here, and this will react over here like that. So with this, you will have Br2 and that will be connected to the FeVr3. Then this will have a positive charge. This will house a negative charge over here, if you can see that. And so, next, this group is going to kick off that Br, and that's just going to form this very strong positive charge on this one Br over here. And it's also going to form FeVr4, but with a negative charge over there. So that would be the conjugate base. So that's the mechanism for how this works over here. And now let's go back to the benzene ring. So now we have the benzene ring, and it's going to react with this Br that has a positive charge on it. And so this, one of the pi bonds is going to go over here, and it's going to grab that Br. So let's draw that out. I just used that one as an example. And if you go to either one, I'm just going to pick this one right here. And so this one right here is going to have a positive charge because of that, losing that pi bond there. And then I'm going to note that there's also a hydrogen there on the site that where Br attacks or gets added to the benzene ring. And so, using a base, or you could use the conjugate base there, probably makes the most sense. You have FeVr4 with the minus charge. And so this is going to act as a base. It's going to come over, take that hydrogen, and this bond is going to make that pi bond come back. So that'll give us this structure again, but with Br added. So now we have that, and that is that's just this part of the reaction. And now it's going to, this ring right here, benzene ring with the Br, is going to react with the SO3H. So give me a second, I'm going to do that. Okay, so I just cleared some space so we could do the mechanism for this part of the reaction. All right, so now that we have the Br group attached to the benzene, it's going to react with the SO3H, which is what I just drew out here. And so, because bromine is ortho-para-director, it's going to either go onto this part of the ring or this part. I guess it could also be this part as well. But it doesn't matter. It just won't go to the meta-directed site. Okay, so just for this example, let's just take this bond back here. It's going to go and react with the sulfur group, and that double bond is going to go, that lone pair is going to attach the OH there, and that's going to make this. One second. Yeah. So it's just going to go attack and attach there. Oops, sorry, made a mistake. Yeah, so that bond goes away, and there's going to be a partial positive charge there, right on this ring. There's also another hydrogen there as well, just for reference. And so now the ring is going to react with whatever base you happen to have. I'm just going to label it B for now. The base here is going to come, take that hydrogen, and that's going to bring the bond, the pi bond back on that ring. And so for this product, what we're going to get is the Br there, and just to make it easier, I'm going to just write SO3H on the bottom there. And so that's one of the products. However, this one asks for more than one, I guess. So I won't take the time to write out the mechanism for that because it's pretty similar. So it's also going to form a product where it could react with the ortho group instead rather than para. So you could get this product as well. Because it could either be on the para group or the ortho, because bromine is the para director. So this here's our two products that the mechanism had as well. I hope that's helpful. All right, so on to problem 9. This one asks, how would you synthesize this product starting with benzene? All right, so here's our product here. As you can see, what we have is a benzene ring with a nitro group attached and an NH2 or an amine group attached as well. So let's just start with the benzene ring. All right, so how are you going to get both of these substituents on the benzene ring, and specifically in that order where it's in the para format? So first of all, I'm thinking that we're going to need a nitro group. So one of the reactions that we know is if you have concentrated HNO3 on there, then that will do a nitration, and you should get this. Yeah, so that will give us a nitro group on our benzene ring. Now, if we decided to do that again, do another nitration, what we would get is another nitro group, but in the meta position, since NO2 is a meta director. So, in order to prevent that from happening, what we're going to want to do is first go through the whole condensation reaction, so the H2 PD sort of reaction, or you could use the SN other one as well, whatever works. But what you're going to want to do is just get that reaction so that this nitro group will instead turn into the amine group, which is what we want up here. So now that it's an NH2 group on that benzene ring, that is an ortho-para director. So we can now do another nitration to form the product that we want. So concentrated HNO3, again, make sure that you know it's a low temperature, so it will work that way. And that should give us the product. NH2 up here and NO2 down here. So not that bad. This is how you'd be able to synthesize this product. I hope that's clear. Alright, so our last problem, problem 10, once again is asking for us to predict the product or products, because there are most likely more than one in this one. Alright, so our starting material here is two phenyl groups attached to each other. And so and then our reactants is I2, so two iodine atoms with FeI3. So this one, we know that phenyl group is ortho-para director. So we can know that the product is going to, with this reaction using Friedel-Crafts acylation, the product is going to have iodine somewhere either in the ortho or para position. So one of our products is going to be this. Sorry, just having to look at it. Okay, so, right, that's going to be one of our products where iodine is going to attach to the ortho position. Now, I don't think it matters where, like, if you put the iodine in this ring or this one, either way, it's not going to matter. And so, but another product that could appear is the one where iodine shows up in the para position. Wow, my drawings are so bad. Anyway, yeah, this is another product that can show up. It's just note that it's not going to go to either this one or up here. These are the meta positions, and since phenol is not a meta activator, meta director, then it's not going to go there. So these two should be the only products that form from it. Let me just show you again. There we go.